This section will set the stage for what I consider the core of statistics, which is inferential statistics. That is estimating population parameter from a small sample. What we see, as I mentioned earlier, every 4 years in the election, and how accurate the estimation of the winner or the loser within perhaps 4 or 5% margin of error. Some people do not even go to vote after they hear the news and they look at the estimation results on TV, because they tend to trust these values very much. Now, that was not always the case. In fact, in past history, there was huge errors in estimating the election results. At some point of time, people will go to sleep thinking that one candidate will win with a landslide, and they wake up finding that it's the other candidate that won with a landslide. So the estimation techniques in the real world have not been all as accurate as we see it in today's practical life. And the reason for that is the technology. The ability to access population, the ability to actually go and entertain different options for states that are already decided, then we move to states that are undecided. We did not know what states that are decided and what states that are undecided in the theories, for example. Now we know. Now we have more information. We have more access and the more information about the populations. So sampling has become a more of a well-developed technology that supported by the very powerful computing facilities we have. In order to understand how we estimate population parameters from sample statistics, we really have to introduce the concept of sampling distributions, because that concept set the stage to the entire subject of inferential statistics. So let's go to the slides and see what is the concept of sampling distributions and what do we mean by sampling distributions. Sampling distributions. As we repeatedly said, we have a population of a size n, and if we have the luxury to access every component of the population, suppose the US population and all people income or whatever or age, then we can calculate the mean of the population, which should be the sum of all the individual observations in the population divided by the total size of the population, the N capital here. And we can calculate the population mean. We can also calculate the standard deviation of the population using the formula that we discussed before, and we can by that obtain the parameters of the population, a measure of the center and the measure of variability, mu and sigma. Unfortunately, that cannot happen in the real world. It's hardly ever happened that we go to the entire population and use the data from the entire population and calculate the mean and the standard deviation. Instead, we take a sample from the population and try to estimate these parameters. Okay? Now, if we could do that, then we will have a whole population distributions. And we need to get familiar with that there is a population distribution. There is a parent distribution representing the whole population that's out there. We may not have access to it, but we need to keep it in mind. Very good. Now, if I take a sample of size n, and if I can repeat that many times, which is actually what happens in the real world, that every day or every week, you take a sample from the population. During the election, for example, we take a sample from the population every month or so, or every time we have a change in people's opinion. And eventually we have many samples where we can calculate their mean. We call it the average of averages, which is the X double bar, and that is the sum of the individual averages. So we're no longer dealing with the individual observations as we did before. We are dealing with the averages. Now, if we take the different averages of the different samples and get the sum of these divided by the number of samples, that's what we mean by K, that will give me X double bar, or the average of averages, or the overall average of samples. And that's very much should be definitely mathematically equal to the population mean. We can also calculate the standard deviation, but this time it's not the standard deviation of the individual observations as we did before. It is the standard deviation of averages. So I'm no longer going to be dealing with the individual observations. I'm going to be dealing with the average values. I calculated the mean of the averages, and now I'm calculating the standard deviation of the averages, which, as you can see here, it's the individual average values minus the overall average of all the averages square, and the sum of that divided by the size K, which is the number of samples, and that gives us sigma x bar. Notice that this is sigma suffix x bar, or the standard deviation of averages, different than the standard deviation of individuals. Very good. We can also construct a distribution of these average values. Now, a minute ago, we told you that if we have the luxury, we can construct a distribution of the whole population. But this one here is different. This one is a histogram constructed from the average values. That's why the horizontal axis here is the average values, and the vertical axis here is the frequency of the average values. That is what we call sampling distribution. So what is a sampling distribution? Sampling distribution is a histogram, essentially a histogram of some sample statistics. We can construct a histogram for the average values of different samples, or we can construct a histogram of the standard deviation of different samples, or the range of different samples. In any case, we will call that a sampling distribution. So what's a sampling distribution? It's a histogram or a frequency distribution of some sample statistics, more commonly the mean value. So once again, we have a population, we took few samples, we calculate the average of each sample, and by comparison, if you had full access to the population and you can calculate the mean of the entire population, here is our average, by example, 35.65. If you calculate the standard deviation of the whole population, you will get a value such as this one here, 6.57. But when you take samples from this population and calculate the average of averages, that is mu or x double bar, you notice here that this value here is still 35.65. What does that mean? It means the average of all observations will be identical or equal to the average of averages of the different samples. Now let's look at the standard deviation. This is the standard deviation of the entire population, 6.57. Now let us look at the standard deviation of the averages. Notice that this standard deviation is much smaller than this. This was 657, this was 294. That's just an example. But if you repeat this for any other types of values or variables, you will get very much the same trend. So what we have here, we have sample averages or the overall average of sample averages is identical to the population average, but the standard deviation of averages is smaller than the standard deviation of the parent population. Graphically, this is how we represent the two distribution. This is the population, the parent population frequency distribution, and this is the sampling distribution or the frequency distribution of averages. Notice that we have here x bar, while here we have x. And you can see that the two distributions share the same average. As you can see, 35.65, 35.65. But the width of the distribution or the extent of variability is different. The parent population has a wider range, wider width, that's why it had larger standard deviation, while the sampling distribution has a narrower range or narrower width. That's why it had a small standard deviation. And all of these concepts are implied in the so-called the central limit theorem. What the central limit theorem tells us is very, very important. It tells us that if we take samples from a population that exhibit values that happen to be normally distributed, can you see that? Then the sampling distribution, that is the distribution or frequency distribution of averages, will also be normally distributed. This is neat. So the distribution of individuals will match the distribution of averages. Very good. So if the variable x in the parent population follows a normal distribution, then the sample mean x bar will also follow a normal distribution. Okay? What if the parent population does not exhibit a normal distribution? It rather exhibit any type, like in this case bimodal, very strange looking distribution here. Well, even with that, the central limit theorem tells us that if you select large enough samples, that's large enough sample sizes, then the distribution of these large samples will follow a normal, or can be approximated by a normal distribution. It's very important to use this theorem because the use of the normal distribution, as we will see later on in the estimation, makes our life much simpler. So two things we've learned so far in the central limit theorem. The first one, if the parent population has a normal distribution, then the sampling distribution